Welcome to my channel. Today we are discussing the very important topic of physical chemistry for IIT JEE mains and advanced point of view. That is very important lesson. States of matter. In these states of matter, in this class we are discussing some important problematic part. Let us consider a one box of capacity 1 liter. A box of capacity 1 liter. It is divided into two halves, which is divided into two equal halves. Suppose in the left side of the vessel containing 16 grams of methane gas. In the right side compartment containing 64 grams of SO2 gas. In the left side compartment 16 grams of methane gas and the right side containing 64 grams of SO2 gas. These divided with a partition simply. And its exerted pressure is supposed P, and its exerted pressure is supposed P. Why it is the same pressure? If you maintain a constant temperature, moles and volume is equal, then pressure is equal. 16 grams of methane, 1 mole. 16 grams of methane, 1 mole. Under a volume 0.5 liter, suppose the temperature is T Kelvin, at that exerted pressure is P. Here 64 grams of SO2, that means again 1 mole of gas and same volume 0.5 liter, this temperature is same, again the pressure is P. Then between the two compartments, if the partition is removed, then what happens? What is the pressure? Initially the left side pressure is P, right side pressure is P. If the partition is removed, then what is the total pressure exerted by the gas mixture? Yes, majority members think like this, sir. This is P and this is P. The total pressure by removing the partition, the total pressure is 2P. Yes, is it equal to total pressure 2P? Yes, that can be explained here. The total moles of the gas, N is equal to N1 plus N2. The total moles of the gas, N is equal to N1 plus N2. We know PV is equal to nRT. If the temperature is constant, then P total and V total is equal to P1 V1 plus P2 V2. P1 V1 plus P2 V2. By using this data, can calculate the total pressure. Total pressure is equal to, yes, the initial pressure P1 in the first compartment is P, and volume is 0.5 liters. And the next compartment, the pressure is again P, and volume is again 0.5 liter. The total volume of the vessel after removing the compartment, this is 1 liter. 0.5 plus 0.5, 1 liter. Then P total is equal to how much? If you common this 0.5, so this is 0.5 is common, P plus P, 2P. 2p into 0.5. Then we got the answer P. Then we got the answer P. This is very important concept. Yes, majority members think like this. So here pressure P is RP. If the compartment partition is removed, then pressure is 2p. Partition is removed, the total pressure is 2p. That is wrong. The total pressure is how much? P. Yes, this is a very important concept. Yes. One more problem related to states of matter. At a constant pressure and moles, initially a gas is present at a temperature 0 degrees centigrade. At a temperature 0 degrees centigrade. At which temperature the volume of the gas becomes doubled. At which temperature the volume of the gas becomes doubled. Here the pressure and the moles are constant. Initially the gas is present at 0 degrees centigrade. At which temperature the volume of the gas is doubled. That means in this problem we want to calculate temperature. Now what is the given condition here? If pressure and moles are constant, then according to Charles' law, V proportional to capital T. This is very important point. Majority of the students are mistaken in this case. Volume is not directly proportional to small t, not temperature in Celsius scale. Volume is directly proportional to absolute temperature, that is Charles' law. So therefore, initially the temperature is given 0 degrees centigrade, volume of the gas is doubled, then at which temperature this one take place, that is the question. Then, so majority members do like this, V proportional to small t. When temperature increases, volume increases. Yes, it is correct. But when temperature in Celsius scale increases, volume is not increases directly proportional. This relation is wrong. According to Charles' law, volume is directly proportional to absolute temperature. According to Charles' law, volume is directly proportional to absolute temperature, not temperature in Celsius scale. So therefore, according to Charles' law, volume is directly proportional to capital T. What is the difference between this and this? Here volume is directly proportional to small t in degrees centigrade. This is wrong. Here volume is directly proportional to capital T, means that is Kelvin. Capital T means Kelvin. Therefore, we apply the relation V1 by V2 is equal to T1 by T2. V1 by V2 is equal to T1 by T2. Yes, in the given problem, at which temperature the volume of the gas becomes doubled. That means initially the volume is V. And the volume becomes doubled. That means 2V. Initially the temperature is 0 degrees centigrade. Don't substitute directly here. That must be converted to Kelvin. Then nearly capital T is equal to 273 Kelvin. Then the temperature T2 is equal to how much? So then we multiply the term. Temperature T2 is equal to 546 Kelvin. 546 Kelvin. Suppose, yes, this is temperature. After calculation of this one, temperature is equal to 546 Kelvin. Suppose this value in degree centigrade is required, then small t is equal to minus 273, that is equal to 273 degrees centigrade. That is one more important problem. As the next concept, find the relative ratio of diffusion. Find the relative ratio of diffusion. Find the relative ratio of diffusion from a container containing a gaseous mixture 2 grams of methane and 16 grams of SO2. A gas mixture 2 grams of methane and 16 grams of SO2 is present in a container. From this gas, find the relative rate of diffusion. How can you find out the relative rate of diffusion? By using the mass, initial mass is given. Yes, this is the formula. A relative ratio of diffusion R1 by R2 is equal to initial moles N1 by N2 into under root M2 by M1. The relative ratio of diffusion, R1 by R2 is equal to initial moles N1 by N2 into under root M2 by M1. R1 by R2 is equal to initial moles N1 by N2 into under root M2 by M1. So here find the initial moles N1. You know N1 is equal to 2 by 16. N2 is equal to 16 by 64. Then I can write 64 by 16. 2 by 16. Weight by molecular weight. 16 by 64. Then I can write 64 into 16. 64 by 16 into under root M2. M2 is the second gas. SO2. That is 64 is the molecular weight. First gas is methane, 2 by 16. Second gas is M2, that is 16. Yes, 16, 64, 4 times root 4. That value is 2. Then this is calculation. 2 into 64 by 16 into 16 into 2. Then which on calculation? 16 in which 4 times. Then 2 by 16, 1 by 8, 4 into 2, 8. Then you got the value 1 is to 1. 1 is to 1. So this is one more important problematic part. As next concept related to Dalton's law. As first to verify related to ideal gas equation, one problem is completed. And second concept we are discussing related to Graham's law. In the next concept we are discussing related to Dalton's law. We know according to Dalton's law, partial pressure of the gas is equal to mole fraction into total pressure. Partial pressure of the gas is equal to mole fraction. Mole fraction means moles of that one by total moles into total pressure. Partial pressure of that gas is equal to moles of that one by total moles into total pressure. Yes, based upon this formula, I give you one problem. A vessel contains 8.8 grams of carbon dioxide. A vessel contains 8.8 grams of carbon dioxide and 3.2 grams of oxygen gas at a constant temperature, and the mixture exerts a pressure, total pressure is 0.6 atm. Then find the individual pressures, nothing but partial pressures. Yes. I want to calculate the partial pressure of carbon dioxide. Before to calculate the partial pressure of carbon dioxide, first we find out moles. Yes. Moles of carbon dioxide, take N1 is equal to weight by molecular weight. That is 0.2 moles. Moles of oxygen we calculate, then that is 3.2 by 32.1 moles. Then I want to calculate partial pressure of carbon dioxide. Is then partial pressure of carbon dioxide is equal to moles of carbon dioxide by total moles, N1 by N1 plus N2 into total pressure. Yes, by using this formula, moles of partial pressure of carbon dioxide is equal to moles of carbon dioxide is 0.2 and the total moles is 0.3 and total pressure is given 0.6. So 0.3, 0.6, 2 times 2 into 0.2, that is 0.4 atm. Yes, you can write the answer here. Partial pressure of carbon dioxide is equal to 0.2 by 0.3 into 0.6. That value is 0.4 atm. And one more important point. To find out partial pressure of oxygen, we use the same formula. Moles of oxygen by the total moles into total pressure. Or otherwise, a container or a vessel contains carbon dioxide, oxygen, only these two gases. Now, according to Darter's law, the total pressure PT is equal to sum of two partial pressures. We know the total pressure. PT value is 0.6, in which one gas pressure is 0.4, and the next gas pressure is automatically P2 is equal to 0.6 minus 0.4, that is 0.2 atm. There is one more simple problem. These are very basic problems. Here we are discussing some basic problems. Here, today in this class, we are discussing some basic problems related to states of matter. Yes. Next concept related to velocities. As we know, a graph is drawn between fraction of molecules versus velocity. A graph is drawn between fraction of molecules versus velocity at a particular temperature. T1, at a particular temperature. Yes, this is at a particular temperature T1. Initially at low velocity, fraction of molecules with that velocity is this much. Velocity increases. Fraction of the molecules with that velocity increases. Velocity increases. Fraction of the molecule with that velocity increases. Velocity increases. Fraction of the molecule with that velocity increases and reach a peak value, and then gradually decreases with increasing of velocity. This is observed at a particular temperature. After that, when temperature increases, what happens? When temperature increases, suppose you maintain the temperature at 27 degrees centigrade This is the graph. If the temperature increased to some 47, 57, 67, like that, what is the graph is observed? Yes, when temperature increases, that is T2. Here, T2 greater than T1. T2 greater than T1. The temperature increases. Fraction of the molecules with the lower velocities decreases. Fraction of the molecules with the lower velocity decreases. But the fraction of molecules with the higher velocity increases. At low velocity, fraction of the molecules are less than the initial temperature. Fraction of the molecules less decrease. And at high velocities, fraction of the molecules are high. And very important, when temperature increases, this graph shifts towards right hand side. This graph shifts towards right hand side. Right hand side. It moves towards right hand side. And one more, height of the graph decreases. Height of the graph decreases. Now based upon this one, I am asking one question. Here, the observed velocity is called most probable velocity. Here also, the observed velocity is the most probable velocity, Cp dash. This is Cp, this is Cp dash. I am asking the question. When temperature increases, the fraction of the molecules which having most probable velocity, increases or decreases. Yes, majority members think like this. Sir, temperature increases, velocity increases. Temperature increases, velocity increases. Yes, it is correct. We observe probable velocity, RMS velocity, average velocity. Any velocity, temperature increases, velocity increases. Correct. But the question is, when temperature increases, fraction of the molecules with the probable velocity. Here the fraction of the molecules with the probable velocity at this temperature is this much. When temperature increases, fraction of the molecules with this temperature is this much. So initially this is the fraction with the T1 temperature. At temperature increases, fraction of the molecules with the higher temperature, what happens? Yes, decreases. That is a very important concept related to fraction of molecules, RMS velocities. Yes, one more concept. We know the formula of root mean square velocity, C RMS. Yes, we know RMS velocity formula is derived from one equation, that is kinetic gas equation. What is kinetic gas equation? PV is equal 1/3 mnc square. Small m c square. In that formula, small m means mass of each gas molecule. Small m is the number of gas molecules. Number of gas molecules, but not moles. PV is equal to 1/3 mnc square. In this formula, majority members think like this. Small n means number of moles. That is wrong. In PV is equal to 1/3 mnc square, small n means number of molecules. And small n is mass of just one molecule. Just one molecule. By using that expression, PV is equal to 1/3 mnc square, to derive RMS velocity, in that case we assume 1 mole of a gas. So for 1 mole of a gas, small n is Avogadro number for 1 mole of a gas. All the number knows for 1 mole molecules is equal to Avogadro number. That means small n is equal to Avogadro number. Then small n into capital N becomes capital N. Then this is the formula, CRMS formula, root 3PV by m. Yes, by using this formula, I am asking a simple question. At a constant temperature, when pressure is doubled, pressure increases or pressure is doubled. At a constant temperature, when pressure increased by 2 times or pressure is doubled, what happens in the RMS velocity? Initially the RMS velocity is c, or initially the RMS velocity is v, or initially the RMS velocity is x. When pressure is doubled at a constant temperature, what happens in the RMS velocity? Yes, majority must think like this. RMS velocity is directly proportional to root P. That means C1 by C2 is equal to root P1 by P2. That means if pressure is doubled, yes, P1 is x, P1 is P, P2 is 2P, then 1 by root 2. Then velocity is equal to root 2 times of c. Yes, somebody doing like that. But the very important, here given at a constant temperature. At a constant temperature, when pressure is doubled, volume is reduced to half. That is Boyle's law. And very important, these are all problems related to ideal gas. In this class, we are discussing the concept related to ideal gas, but not real gas. Here, in this class, total class, I am discussing ideal gas. So, for an ideal gas, at a constant temperature, when pressure is doubled, what happens in the RMS velocity? When pressure is doubled, volume is reduced to half, then this is 2P, V by 2 cancel, again PV remains constant. Therefore, RMS velocity value, no change. There is no change in the RMS value, even pressure is changed at constant temperature. This is very, very important information. So, in this video, we are discussing the problems related to states of matter related to ideal gas. Boyle's law, Charles' law, Avogadro's law, Graham's law, Dalton's law, and kinetic theory of gases, RMS velocities, probable velocity, average velocity. Some concepts are discussed here. It's a brief discussion. I think if you are perfect this video, if you are follow this video, then these are all problems related to gas laws, all related to gas laws and ideal gas equation, Graham's law, Dalton's law. If you follow this video, if you satisfy, then for more videos, in the next video, we are discussing the next topic related to states of matter, related to next real gas equation. Real gas equation. I am discussing in the next video, real gas equation. To get that videos, please subscribe my channel. Okay.